And it was developed by a geologist named Tuzo Wilson. And I really like the Wilson cycle, even if it may not be true, but it puts together the theory of seafloor spreading, with the seafloors opening up and pushing the continents around, which is called continental drift. It puts it into a cycle, which is very intriguing. The basic import of the cycle is that if we think of our globe, where you have the continent of Africa and Eurasia on one side, so this is Eurasia and Africa on this side, and on the other side you have North America and South America. These are the continents. Then what the Wilson cycle is suggesting is that the seafloors open on either side of the earth. These continents are doing this, back and forth like windshield wipers. And it's been through about 3 cycles in the history of the earth. It begins as Gondwana land, then it opens up and it eventually collides on the other side as Pangea, and now it's opening up again. As it opens up again, it forms the Atlantic Ocean on one side and the Pacific Ocean on the other side. So if it's true, it means the earth is very ancient and God has placed like windshield wipers on the earth as it goes back and forth, as sea floor opens up on one side and is destroyed on the other side, and so on. And so I created a series of block diagrams to illustrate this to my classes. Now that it's digitized, I can put it into a format where I can show you the blocks in sequence. So the first stage is where this hot mantle fountain or plume comes through from the core of the earth. It heats up the base of the lithosphere, the earth's crust. As things heat up, they expand. And as they expand, it creates this dome at the surface. And as a dome forms, there's naturally going to be extensive forces in the top of the dome, which create these 3 radiating fractures. So at the end of class last time, we went to the Colorado Plateau in the western United States and saw the Grand Canyon. We also talked about some of the other canyons, such as Bryce Canyon. And geologists believe that's what's happening at the Grand Canyon right now, that the Colorado Plateau is a giant dome that's forming. And as it begins to move upward, the Grand Canyon is not this fracture. That's something that occurs later. The Grand Canyon is caused by the Colorado River that's just trying to cut back down through this rising dome. All right, so the second stage, you move from the initial doming to a linear ocean basin that forms. And so whenever this fracture grows, you can see 2 of the fractures have continued to grow. One of them, this one on the right, stops growing. They call that an allocogen, or a failed arm. These allocogens become conduits for major river systems. So if we think about the Mississippi River or the Niger River in Africa, you're actually looking at rivers that are flowing into this failed arm. Okay, so whenever the fracture continues to grow and it eventually connects to an ocean, it will fill with water and create this long linear ocean basin. Where they think this is occurring is in Africa, the eastern part of Africa called the Ethiopian highlands. You can actually see these long linear ocean basins like the Red Sea and the Gulf of Aden. So according to geologists, there is a dome that formed here called the Ethiopian highlands. It began much like the Colorado Plateau, but in this case, it's continued to grow to where those 3 radiating fractures have grown to large linear seas. And so you have a fracture here that forms the Red Sea. You have a fracture there that forms the Gulf of Aden. And then you have a fracture here that's the allocogen, the failed arm, which is called the East African Rift System. The next stage is for the ocean basin to continue to grow into what is called a passive ocean basin. A good example of this part of the Wilson cycle would be the Atlantic Ocean. According to geologists, the Atlantic Ocean is still coupled, like train cars that are coupled together. It's still coupled to the continental lithosphere. And so as the ocean basin opens up, it pushes the continents apart. Because they're still coupled together, there's no subduction zone. There's no building of stresses and strains. There's no melting rock to form volcanoes. Therefore, along the eastern seaboard of the United States, if you go to North Carolina and South Carolina and Maryland and so on, along the coast, you don't find volcanoes, and there's not major earthquakes there because the continent and the oceanic floor are still connected. So we look at the Atlantic, you can see the oceanic ridge system down the middle, and you can see sediments coming off the continents here, forming these wedges of sediment beyond the shelf, but there's no subduction in the area. As these passive ocean basins begin to grow larger, the rock is cooling and condensing and contracting. And so along these edges, these passive margins, the rock begins to break away from the continents. This is especially the case whenever an ocean basin is opening up on the other side of the earth. It creates compressional forces that will cause a fracture. In other words, the train cars become uncoupled. And when that occurs, you have a different type of ocean basin. They call this an active ocean basin. So passive is where you don't have volcanoes and earthquakes. Active ocean basins are where you do. And according to plate tectonics, the reason you see earthquakes and all these volcanoes is because now the ocean floor is being shoved back down into the Earth's interior. As it descends, it gets hotter, and the silicate minerals begin to melt. Silicate minerals melt at a lower temperature than non-silicate minerals. I think I mentioned this before. You can think of it like a chocolate chip cookie, where the cookie itself is the non-silicate and the chocolate chips are the silicate. And so, like you have a chocolate chip cookie out in the sun, the chocolate chips begin to melt out. Well, that's what's happening here. The chocolate chips, the silicates are melting out, and because they're heated and they're expanded, they rise. And what geologists call a diapir. If you've ever seen a lava lamp, you've seen beautiful examples of these diapirs as this glob of oil moves upward. That's what's happening here. When it reaches the surface, the magma forms a chain of volcanoes. You see them here? And geologists call that island arc systems along this subduction zone. You also have a deep ocean trench. The deep sea trenches are where this oceanic lithosphere has been bent downward back into the interior. So earthquakes occur along this edge as the two plates rub together, and volcanoes form from the melting oceanic lithosphere. And they call that an active ocean basin. So when you look at earthquake distribution here on planet Earth, you can see most of the earthquakes occur along the Pacific coast. The reason is because it's an active ocean basin, and that's where the oceanic lithosphere is rubbing up against the continents as it descends back into the Earth's mantle. When we look at the Atlantic, there's very few earthquakes along the coast because it's not decoupled. So passive ocean basin, Atlantic, active ocean basin, Pacific. It's part of the Wilson cycle, and as the Atlantic opens up, it's pushing the continents apart. It's actually pushing these continents over the descending Pacific plate. And eventually, according to the Wilson cycle, North America and Eurasia will collide with each other and form another giant landmass. All right, so we're looking at the different stages of the Wilson cycle. We go from a passive ocean basin to an active ocean basin, and then that ocean basin will eventually be swallowed, as you see here, as the continents come back together, and they will eventually collide. When they collide, they create a mountain system, what geologists call fold mountain belts. Ultimately, there are two basic types of mountains: fold mountain belts, where continents collide, and volcanic mountains, where molten material is being ejected onto the surface of the earth and piling up. All right, there is a stage whenever the continents first come back together that a portion of the sea floor can be ripped off, cut off by the pinching effect of the two continents. This is, I'm using this as an example of how the theory of plate tectonics very good at explaining anomalies, things that geologists could not explain with other models. That's one of the reasons plate tectonics is accepted as the paradigm of geology today. And one of those, a good example of one of those anomalies is something called an ophiolite. Ophiolite is a section of rock that may be 20 or 30 miles long and 10 miles wide that they find in the top of the mountains, but it doesn't look like any of the other rocks on the mountains. It's completely different, completely out of place. And ophiolites always have the same structure. It's a series of basaltic volcanic rocks that are what they call a sheeted dike complex. They've been injected into each other in a series of vertical layers. It's identical to the type of rock that geologists find when they drill into the ocean floor. So what they discovered is that there's a large section of ocean floor, 10, 15, 20 miles wide, 30 or 40 miles long, a piece of ocean floor on the tops of mountains. And the question was, how in the world did it get there? And they didn't know. It didn't make any sense. However, in plate tectonics, you have a way of explaining that. As these two continents come back together, they rip off a piece. You see it there? They rip off a piece of the ocean floor, and that becomes part of the mountains. It's a very painful illustration, but I think its painfulness may make it effective. Have you ever had a zipper and you're zipping and your skin gets caught in the zipper and you immediately stop? Because that's going to really hurt if you keep trying to zip it up with a piece of skin in your zipper. Well, what if you didn't stop? Well, it would be an ophiolite. That's what's happening here. A piece of skin is caught in the zipper, and as it comes together, it rips off that layer and it incorporates it into the mountain structure. This is an aerial photograph showing this. Do you see this dark layer here? That's ocean floor. That's an ophiolite, and it's actually resting on top of these other sedimentary structures. This is a close-up that was taken of that very ophiolite in Oman. And you can see the pillow lavas, and you can see how they've been injected into these fractures in a vertical sense. It's the exact same formation you see developing in these mid-oceanic ridges. And so it's a piece of ocean floor, essentially. All right, so the two continents are a passive ocean basin. They're moving away from each other. Then they begin to move back toward each other as subduction zones form in a active ocean basin, and they come together and they collide. And like two cars colliding, they crumple together. It creates a massive pile of material. Not only does material pile upward to form the mountains that we see, but there's also a very large amount of material that's pushed downward into the mantle. What that means is mountains have roots and this thickening that occurs. And the look of the rocks within the mountains is depend to a large extent on the pressure that they're experiencing. So for instance, if we go to the top of the mountains, they're experiencing low pressure because they're at the surface. And rocks at the surface under low pressure, whenever they're compressed, they break, they splinter, like dropping peanut brittle on the floor. It's extremely brittle. Rocks in low pressure are brittle, and we know that. You can hit a rock with a hammer and it breaks, it fractures. What you may not know is that when you put rocks under tremendous pressure, as you would find deep inside of these mountains, they don't behave as brittle solids. They behave as plastic material, like silly putty or taffy or very cold syrup. They flow very slowly. And so in the interior of the mountains, you can see these folds that are forming. At the very base of the mountains, deep in the roots, the temperatures are so high that the rocks actually begin to recrystallize. They begin to form into other rocks called metamorphic rocks. And deep at the down at the very bottom of the mountains is so hot that the rocks are actually melting. And as they melt, they form these diapirs that we talked about, like lava lamps, molten rock that's moving up, and it cools and it becomes part of the roots of the mountains. they call those large granite bodies plutons. So you see the plutons that are embedded in this soft metamorphic rock. All right, so the three parts of the anatomy of a mountain: brittle solids and lots of faults and fractures at the surface, taffy-like folds in the middle, and at the very bottom, metamorphic rocks with big chunks of granite that have crystallized in. All right, I want to show you a place on Earth where they believe that mountains are forming, in the process of forming, as continents collide. It's actually the microcontinent of India. According to plate tectonics theory, India was once a part of Antarctica, and it actually broke away and it moved northward through the Indian Ocean and eventually collides with Eurasia. And you can see the mountain ranges forming here that forms the Himalayas primarily. All right, if you look at the ocean floor, you can even see the transform faults that geologists believe are the tracks of the movement of India northward as a microcontinent. As you know, I love Google Earth, and so I can actually build a flight where we can go down to the Indian continent, and it does look like someone stumped their toe on a rug or something. You can see the folds that are developing to the north of India. So we're following the Himalayas as it goes up above the snow line. You can see the snow caps there of the Himalayan mountains. And behind it, you can see what they call the Tibetan Plateau rising. And they believe that the mountains there are in the process of rising a few inches every year. The very highest part of the Himalayan range is Mount Everest. So it's between 28 and 29,000 feet, I believe, is the altitude. So there's Mount Everest, highest peak on Earth right here. The highest place you can go and stand. Of course, everybody wants to go there now. Summit Mount Everest. We can follow the Himalayan range continuing to the east toward the Ganges and the Brahmaputra rivers, and then south toward Indochina. You can even see the faults here, splay faults. And Indochina is like a material that's being squirted out. It's they actually created a model called the indenter model, and were able to reproduce the geography. All right, so this is what we're looking at, the microcontinent of India that's collided and created not only the Himalayas here, but you can see the Ural Mountains. This is buckle zone that goes up into Russia. Himalayas from the space shuttle. And flying over it in a commuter plane, looking down on Mount Everest. This is a view from the summit. People making the final approach. Actually, from the summit of Mount Everest, you can see how the horizon's curved. So you're so high, you can begin to see the curvature of the Earth. All right, so we're looking at the mountains now. We begin with fold mountain belts. The Himalayas are in the process of forming. As the mountains begin to erode, material is removed from the tops of the mountains through precipitation, glaciers, abrading the rocks, and the rivers carrying them down to the sea. We'll get mountains that are a little bit lower, not the Himalayas, they're the highest, but mountains that are no longer forming, but they're still early in their life. This would be mountains like the Rocky Mountains in the United States. This is Grand Tetons near Jackson Hole in Wyoming. So it's a bit lower mountains, Grand Tetons. If we were speaking French, you'd probably be giggling now. The mountains were named by a bunch of lonely fur traders looking at the mountains, so you could probably guess what it means in French. The rivers are carrying the mountains sand grain by sand grain and throwing them into the sea, essentially. When Jesus says we have to grade faith of a grain of mustard seed, you can say this mountain be removed, it'll be picked up and thrown into the sea. He's actually talking about what geology does. If you wait long enough, all the mountains are being thrown into the sea by the river systems. And because of that, the mountains are sinking, they're getting lower. So you have the collision that forms the mountains, and then erosion erodes them down into the interior. The process that occurs in the mountains is called the isostatic rebound. One of the ways to explain isostatic rebound would be, imagine that you're at a swimming pool and you have one of those really cheap air rafts that you blew up, and you're laying on it very carefully. And then someone brings out their theological library, all of Erickson's systematic theology, and they begin placing it on top of you. Well, as they place those books on top of you, you're going to sink deeper and deeper into the pool. So you're not going to have mountain of books on top of you, but your body's going to be pushed down into the pool. Well, if people begin to take those books off, as they took the books off, your body would begin to rise. It would begin to rebound. That's isostatic rebound. So as material is removed from the summit of the mountains themselves gradually begin to rise, begin to rebound. And so eventually what was once inside of the mountains will be exposed at the surface. And so those folds that occurred deep inside the mountains when the rocks were under tremendous pressure and they begin to bend and shape, now you can see them as erosional features on the surface. This stage of the Wilson cycle are called the, well, in the US, these mountain ranges would be called things like the Appalachians and the Smoky Mountains. We were dealing with a fairly old mountain range, a range that has been eroded down to the middle section of the mountains. So this is the Rockies here, and these are the Appalachians in the north and the Smokies in the south. Actually, I'm not sure if this image will show it. Yeah, I guess it shows a little bit. You can see the Appalachians here, the buckle zone, and the Smokies. The feature you see here is what they call the Delta, the Mississippi Delta, and it's sediment that's been that's buried this old mountain system. So the sediment is on the top of those mountains. However, it comes out here in Arkansas. These are known as, anybody from Arkansas? Called the Ozarks. The Ozarks, the Ouachitas, and the Wichitas, and the Arbuckle. So the Ozarks, the Ouachitas, Wichitas, and the Arbuckle here are actually a continuation of this same mountain range. And it goes underneath the Cretaceous strata here, all the way down to what they call the Llano Uplift area, in this area, which is part of it. So you can see that same buckle zone in Texas. Yeah, I forgot I had a larger image just for that. Not quite as clear. Whenever there's snowfall in the Northeast, what they call a nor'easter, you can actually see the folds, erosional folds, much better exposed at the surface. Yeah, here we go. It would be like taking several layers of rugs and folding them, maybe making a roll of them, and then taking a chainsaw and cutting through them. You would see the different layers of the rugs. All right, so with Google Earth, I can take you down and actually show you the Smokies there, and then travel northward. You're looking at dissected folds. and the rock, and then up into the Appalachians. Where you see these points forming, that's where the folds are plunging. So if I have a rock and I fold it, and then I plunge it towards you, and then we cut through it, it's going to form a nose feature. That's what you're seeing here. And the folds plunge toward the nose. So when you're looking at this fold, it's plunging toward us, whereas that fold's plunging away from us. All right, just showing you some of the erosional features there. When you go to drier areas such as the Zagros, you can even see the folds themselves in the rocks where they're bent upward. Most of them are long linear features. However, there is a fold mountain that was produced by a magma chamber below it in the Sahara that created a perfect circle. It's kind of cool. I think they call it the Eye of the Sahara. But it's the same principle. You folded the rocks into a dome and then you cut through it. You can see the folds in microcosm when you go into these fold mountain belts. And so you take your hammer, you smash it into the rock and it breaks like peanut brittle. And you ask the question, how did such a brittle rock fold? And the answer is, when this rock folded, it was deep inside of the earth under tremendous pressure, where rocks do behave as a plastic and can bend. You've done it in the laboratory. You take a rock and put it under tremendous directional pressure, and then you change the direction and it will bend, just like this. Fold mountain belts. So the erosion is from the surface, and the isostatic adjustment rebound brings the interior of the mountain to the surface, and eventually it will bring the lowest, the roots of the mountains will be near the surface. And they call that a Piedmont area, where you just have a very flat metamorphic terrain, and you see these big domes of granite, which are the tops of these plutons that I mentioned earlier exposed. There are sections along the Appalachians, especially to the east, where you have the Piedmont area, and you can see this feature of the Wilson cycle. This is the Appalachian, what they call the Blue Ridge area, the Appalachian Mountains. And you can see it's just rolling hills that are part of the Piedmont. But out in the rolling hills, ever so often, you'll have one of these big granite domes sticking up out of it. That's one of those plutons. There's actually one in Texas near Fredericksburg, between Fredericksburg and the Llano Uplift. They call it Enchanted Rock. You can go there and see it, but just this big dome of granite sticking up out of the ground. At one time, it was molten rock deep in the roots of a mountain, and it crystallized into granite. And granite's very resistant, so as it weathers, it forms these domes. The most famous is Stone Mountain, Georgia, where they've carved a carving of the, I think, General Lee or something. Stone Mountain, Georgia. All right, so the final erosion back to a Piedmont peneplain, and then the Wilson cycle starts over again. So doming, opening into a long linear sea, continue to increase into a passive ocean basin, then a subduction zone forms, the continents move in the opposite direction, begin swallowing the ocean basin, they come back together, creating a mountain range, and then the mountain range erodes back to where we were at the start, and it begins all over again, the Wilson cycle. Whether it's true or not, I don't know, but it is a cool idea anyway. All right, when we look at a geologic map of North America, the geology is really fairly simple. You can see the material here that's part of the Cretaceous and Pleistocene material has been deposited. You can see remnants of it here in the Rocky Mountains. However, when you get up into Canada, you can see where the ice sheet, glacial ice, has pretty much scraped all the sediment off and revealed basement rock. In other words, this is the deepest rock on the earth, the deepest and the oldest rock you see here. It's like a giant snowplow that just plowed away the snow, and you can see the pavement, the basement. And what's fascinating when you look at the Canadian Shield, you see this purple zone here, and then you have a blue zone behind it. Then you have a yellow, you see it there? You have the yellow, then you have the red, and then the pink. So you see 1, 2, 3, 4 different layers. It's quite possible that that is an evidence of the windshield wiper effect I talked about earlier. Because as the continents move back and forth, the island arc system, the chocolate chips that are added to the edge of the continent, they actually become part of the continent itself. They become accreted to the continent edges. And when the mountains come back together, when the mountains are formed, it compacts those into what geologists call microcontinents. And they're accreted. The microcontinents are accreted to the edges of the continents, and that's how they grow. That's how they build. In terms of our analogy with the windshield wipers, I know this is gross, but I'm trying to help you understand the process. Imagine you're driving through Kansas, out in the wheat fields or the cornfields, and they're having a problem with grasshoppers, locusts. So you're driving at highway speed, 70, 80 miles an hour, and these grasshoppers are hitting your windshield and splattering all over your windshield. And so you turn on your windshield wiper. So when you turn on your windshield wiper, it actually scrapes all of the fragments of grasshoppers to one side, and it forms a layer. As it's moving across, it forms a layer of grasshoppers. And then when it hits the bottom, it compacts those grasshoppers together. And you can see again. So you drive further down the road and you get more grasshoppers. And so you turn it on again and it scrapes all those grasshoppers off, and it's forming this long linear continent of a microcontinent of grasshoppers. And then it smashes and compacts it down into the other layer. So this happens 3 or 4 times, and you get on the other side, you pull into the gas station, you look, and you have these layers of crushed grasshoppers. Geologists believe that's the way continents form, is these windshield wipers are going back and forth, it's scraping off those island arc systems, and it's compacting it on the edge of the continents, and then it breaks apart. And so you see these layers. And geologists think that's what you're looking at here. From the purple to the blue to the yellow to the red, you're looking at those layers of grasshoppers, or the basement rock that was formed. Like I said, I don't necessarily want you guys to believe this. I think it's a very beautiful idea. I think it could be true if the Earth's very ancient. But I still want you to understand this is just theory. We're in the realm of theory now. I'm not teaching how the world really is.